Okay, welcome everyone to Physics 390 class 29. This class is on mixed states and the density matrix. So mixed states are states where, in addition to the uncertainty which we have from quantum mechanics, because of the intrinsic probabilistic nature of quantum mechanics, we actually have a more regular classical probabilities. So for example, if we had a source of silver atoms, which could come out of an oven, creating silver atoms with either spin up or spin down, then we'd have a 50% chance of each of the silver atoms coming out as spin up or spin down. And that wouldn't be a quantum uncertainty. That would be a regular, you could say classical or just regular uncertainty. There's just a probability of the spin up state and a probability of the spin down state. And it doesn't have to do with a quantum uncertainty having to do with the uncertainty principle or probabilistic distributions. So mixed states enable us to take those cases where we have different quantum states as simultaneous possibilities into account. And the density matrix is another formulation. The density operator and the density matrix is another formulation of quantum mechanics, which nicely incorporates mixed states. And we'll also find that the density matrix and density operator are very compatible with thermal and statistical physics. And so they find a lot of application to real world systems where temperature is a factor. Okay, so this material is from chapter 12.3 of our textbook. Let's dive right in. So another formulation of quantum mechanics. So far, we've dealt with pure states, psi. For example, eigenstates of the infinite square well, ISW, or the harmonic oscillator. We've used the time-independent Schrodinger equation and time-dependent Schrodinger equation to find and evolve, respectively, these states. And then we have rules to extract physical properties from the states we get. For example, the psi squared psi is the probability, or we have expectation values for finding the momentum and position of given states. And that's an excellent and fine and good. This is just another, we're going to just look here at another possibility for a way to formulate quantum mechanics, which has certain other advantages in some situations. So another way to formulate quantum mechanics is via the density operator, rho hat, rho for density and hat for operator, which is equal to the projection operator of psi, ket psi, bra psi. So, and we'll look at those properties in a second. So, or why we might want to do this. So in a given basis, which we'll call EI for the Hilbert space, we can write the density operator as a density matrix. So we take the density operator and we sandwich it between a bra EI and a ket EJ, and we get rho IJ. So we get a matrix, which then would be putting in rho here, psi, psi. We get EI psi inner product, psi EJ inner product. So that's the density matrix. So it turns out for density matrices formed from pure states, so if we have a pure state here, like the eigenstates, as I said, of the infinite square well or the harmonic oscillator, or just the pure spin up state is a pure state. There's another example. It turns out we have the properties that the trace of the density matrix is 1. The trace means the sum of all the elements on the principal row, on the principal diagonal, rather, is 1. And the expectation value of an operator, A, which could be the position, could be the momentum, could be angular momentum, could be energy, turns out to be the trace of the product of rho times A, the density operator times the operator we're interested in, and take the trace of that matrix, gives the expectation value. So that's a really nice expression. And then finally, for density matrix formed from pure states, we have that rho squared is equal to rho. Okay, that's known as the idempotent property, just for those of you who like to keep unusual terms in your head. Okay, so let's take an example. So just to see some of these properties in action. So we have, consider an electron in the SX spin up state. So in the SC, written in the SC basis. So the SX spin up state is 1 over square root of 2, 1 over square root of 2, spin up, spin down components in the SC basis. So this is the spinner representing the spin up state in X. So in that basis, the density matrix would be, according to this formula here, psi psi. So that would be row or column vector 1 over root 2, 1 over root 2 times the row vector 1 over root 2, root 2. That gives a actually a matrix, which would be 1/2, 1/2, 1/2, 1/2. So that would be the density matrix associated with this SX spin up state, the pure state. Notice that trace of rho is equal to 1, because if we add the elements along the diagonal, we get 1/2 plus 1/2, which is 1. So that's indeed true. And also that if we take rho squared, which would be this rho times itself, rho squared, that would be 1/2, 1/2 times 1/2, 1/2, which is 1/4 plus 1/4 is 1/2, and we get that for each element. So we just get 1/2, 1/2, 1/2, 1/2 back again, which is rho. So we see that we do verify the property, since we form this density matrix from a pure state, that rho squared equal rho. Okay, now the TDSE, IH bar d psi dt equals h psi, in terms of pure state psi, or wave function psi, can be reformulated in terms of the density operator. It looks somewhat similar. We have IH bar d density operator dt, but then it turns out to be the commutator of H and the density operator. Okay, and that can be proved. So this is equivalent to the time-dependent Schrodinger equation. So this density operator formulation is a full-fledged version of quantum mechanics. We can represent any pure state that we've had so far as a density operator or a density matrix, and then we can see how that evolves in time, and we know how to use the density operator or to extract physical information using the expectation value is trace of the density operator times whatever we're interested in getting the physical information or properties about. Okay, so that's another formulation of quantum mechanics, kind of cool. So what is it mainly used for, first of all? Well, that's this slide, mixed states in thermal physics. So what is a mixed state? A mixed state is a state with a given probability, pk, of being in each of a collection of pure states psi k. So as an example, suppose we had this, going back to what I was mentioning before, we have a source of silver atoms, which can be either spin up or spin down. We would have a half probability of being in the pure state spin up, and a half probability of being in the pure state spin down. So that would be a mixed state. So there's a classical probability pk of being in the each quantum state psi k. So the expectation value of an operator A then becomes the sum over k, all the components of the mixed state, of the probability of each mixed state, times the expectation value for each of those pure states associated with each component of the mixed state in the operator, the expectation of the value of the operator A in that state. So this is a generalization of the expectation value to mixed states, where we just put the classical probability pk in front of our hopefully familiar expression for the expectation value of the pure state psi k, and then sum up over all k. Okay, so we can write a more general density operator to allow for mixed states. And it's maybe, if you thought about it, it's probably what you would come up with. The density operator is the sum over k of the probability pk of each given pure state times the projection operator into that pure state. So this is the density operator for a mixed state with made up of pure state psi k, each with probability pk. And then that leads to the density matrix. If we take the matrix element with EI, EJ as the basis, we get sum over k pk, and then EI psi k inner product, psi k EJ inner product. So we get the density matrix here. Okay, so so that's a more general formulation, which allows us to again build in these classical probabilities and uncertainties we may have about what exact quantum state our system is in, independent. And that uncertainty is independent of the quantum uncertainty, which comes with even a pure state from the just probabilistic nature of quantum mechanics. So anyway, we find that as for a density matrix built from one pure state that we looked at previously, we have for the density matrices built from mixed states, we have the trace of rho equal 1, and the expectation value of an operator A is still the trace of the density operator times A. But it turns out we no longer have rho squared is equal to rho for mixed states. And this is a really nice way to distinguish in this density operator, density matrix formulation, if the state we're looking at is a pure state, or came from a pure state, or came from a mixed state. If rho squared is equal to rho, it came from a pure state. If rho squared is not equal to rho, it came from a mixed state. So let's take a quick look at an example. So consider the density matrix built from SZ spin up and spin down with equal probabilities. So that would be SZ up is 1, 0, and SZ spin down is 0, 1. And they each have a probability of a half. So our density matrix would be sum over k, pk, psi k, psi k. So for example, for the spin up state, we have a probability of a half. Psi k is 1, 0. Psi k bra is 1, 0 this way. And multiplying those out, we get 1/2, 0, 0, 0, 0. Then we look at the spin down state as the part of the mixed state. That has probability a half. Spin down is 0, 1, 0, 1. Multiply that out, we get 0, 0, 0, 1/2. And we get our final state, which is 1/2, 1/2, 0, 0. Okay, so the trace of that density matrix is 1, because the trace of the sum of the diagonals is 1. So that property still holds. However, if we look at rho squared, that would be 1/2, 1/2 times 1/2, 1/2, which would be 1/4, 1/4, which is not equal to rho. So we can see that when we square the density matrix of a mixed state, like this mixed state of spin up and spin down, we do not get back the density operator. And again, that's a good indicator of whether we were dealing with a density matrix built from a pure state, or from a mixed state. Okay, so the final thing we'll note is that the use of the mixed state density matrices is extremely helpful in thermal physics, because quantum states in thermal physics are populated according to Boltzmann probabilities. Now, we're not assuming in this particular class that everyone is familiar with a Boltzmann probability, but it's basically telling us at a given temperature, if the state has a given energy, how likely it is for that state to be populated, and how the relative likelihoods of different energy states at a given temperature. So, and that's the bread and butter, one of the bread and butters of thermal physics is these Boltzmann probabilities. So, so we can, and those are classical probabilities. So we might have, for example, just to give a definite example, we might have a hydrogen atom at a sort of an elevated temperature, for example, in the outer atmosphere of the sun. And so there'd be some probability of it being in its ground state, but some non-appreciable probability of it being in its excited states. And those are classical probabilities, which we'd find from the Boltzmann probabilities using the temperature that it's at and the energies of those different states. So our quantum description of that hydrogen atom in the atmosphere of the sun would be a mixed state density matrix. And then quantum statistical mechanics, which gives us all kinds of tools to figure out equations of state and cool thermal properties and response functions and stuff, is formulated largely in terms of the density operator and density matrix, because it allows us to build in these thermal Boltzmann probabilities very readily. Okay. So just to sum up, we have looked at seen that we've used pure state so far in formulating our quantum mechanics, but the time-dependent Schrodinger equation. But we can see that we can reformulate. It's possible to reformulate our quantum mechanics in terms of a density operator and a which can be the time-dependent Schrodinger equation can be reformulated in terms of that density operator. And then the density operator allows for both pure states and mixed states. Mixed states where classical probabilities figure in. And the classical probabilities figure in very usefully in thermal physics, where again, these thermal probabilities figure in classically. And so we can have quantum statistical mechanics, and which gives us a great insight into the collective behavior of quantum systems. Okay, so I hope that was interesting for an alternative formulation of quantum mechanics, this density operator and density matrix formulation. And thank you for your attention, and I will see you in class.